Hi everybody, this is Dr. Bricker here with a review for Exam 3. So the exam covers Chapter 18, which is Geometric Optics. So there'll be 3 questions from Chapter 18, things like Snell's Law, lenses and mirrors. And for reference, this was from Homework 7. Then we went to Chapter 17, which is Wave Optics, things like index of refraction, how that affects the wavelength and speed of a wave going through a substance. We talked about thin films and double slit. We talked about more than that, but this is what you should focus on for the exam. And then this covers homework 8. And then we jumped up to quantum physics. So there's a couple of questions, 2 questions from this chapter, and things like the photoelectric effect and the de Broglie wavelength. And we'll get into these subjects in more detail. I'm just giving you kind of an overview. And that was on homework 9. And then the most recent thing we've talked about, Chapter 29, which is on atoms and molecules. And for the exam, focus on emission spectrum. So when electron goes from a higher energy state to a lower energy state, emits a photon. What are the wavelengths associated with that? So more about that in just a minute. And then the very last thing we talked about was principal quantum numbers in respect to the hydrogen atom. So we talked about little n, L, M, M sub s. Again, more about that in just a minute. And that was homework 10. So there's 10 questions altogether, 3 from Chapter 18. So 1 on Snell's Law, 1 on lenses, 1 on mirrors. 3 from Chapter 17. So this index of refraction idea, thin films, and double slit. We covered more than that, but that's what the test focused on. And then Chapter 28, we got a couple of questions, 1 on the photoelectric effect, 1 on de Broglie wavelength, and then from Chapter 29, also 2 more questions, 1 on the emission spectrum and 1 on possible quantum numbers. Okay, so 10 questions in all. So you get an hour and 40 minutes to do this. Let's look at these subjects in more detail. Okay, before I get into Snell's Law, I think a great way to study for this, make your own formula sheet, cheat sheet, whatever you want to call it, so you're ready to go. And a great way to study for this is to go back and look at all the homework assignments. I mean, there's 4 of them. It's kind of a lot of material. But when I made the test, I used the homework as kind of a guide. So you won't see the exact questions probably, but some very similar to that. And you could even narrow it down more because I've given you the exact 10 subjects that it's over. So take a look at that. You're looking at the video. That's a good place to start as well. But make sure you take a look at the homework. Go back through the content videos if you have a chance. Read the summaries at the end of the chapter, that sort of thing. Okay, good. So Snell's Law, this is geometric optics. So here's the incident ray coming into the interface between one material. So N1 corresponds to some material. It could be air, could be something else, hitting the interface, and the ray actually refracts like this. So this is the incident angle, theta 1. This is the angle of refraction here, theta 2. So Snell's Law determines how much this ray will actually bend, and we did a nice lab on this. So in this example, N2 is bigger than N1. That's why the ray is moving towards the normal. So one thing to be careful of, all these angles are measured relative to the normal. So here's the normal to the surface, and these angles are measured relative to the normal. So you'll definitely see a Snell's Law question on the test. Okay, and also from the same chapter, we looked at lenses and mirrors. So go back through all that information. We did some ray tracing. So take a look back at that. The test won't actually ask you to do any ray tracing, but it helps you to solve some problems. But you will use the lens maker's equation, which also works for mirrors. So 1 over s prime plus 1 over s is equal to 1 over f. So s is the object distance, s prime is the image distance, and then f is the focal length. So for lenses and mirrors, you've got this equation, and then you also have the magnification equation. So m here is magnification, minus s prime over s, which is equal to minus s prime over h, which is equal to h prime over h then. So this is the image height, this is the object height. Okay? So when you look through this chapter, there's in the summary section a nice little table of what does it mean when S prime is positive when S prime is negative. What does it mean when F is positive and negative, that sort of thing. So make sure you go back and review that. S, it turns out, is always positive. So that positive always. S prime can be positive or negative. So I didn't fill in this whole table here. Make sure you go back and look at that. And then F, the focal length is positive for a converging lens or a concave mirror. So converging lens is this shape, concave mirror is this shape, and here's the object. It's always negative for a diverging lens, so a diverging lens looks like this, or a convex mirror. So if the object is over here, that's a convex mirror. Okay, reminder, S prime is, if it's positive, so if S prime is positive, that means you have a real image. Real images are always inverted. If S prime is negative, the image is virtual. Virtual images are always upright. So you'll never have a real upright image. Those don't go together. These go together, and these go together. So time-wise, this is the thing that we did, maybe about a month ago or so. So this might be less familiar, but hopefully it's ringing a bell. So again, go back and look through the problems from the homework that we did, both for Snell's law and also for lenses and mirrors. So you'll see one lens. I'm not going to tell you which one, either converging or diverging, and then you'll see one mirror problem. The nice thing is, if it's a lens or mirror problem, here's the equations that you have. And then to kind of help you out, make sure you know what the S prime, positive, negative, F, positive, negative, all that sort of thing, how that works together. Okay. Then we went backwards to chapter 17, and we looked at homework 8. So index of refraction here. There's an index of refraction question. So when a ray of light enters a material, it actually slows down. That's what the index of refraction originally came from when we talked about it. So this would be the speed of light divided by the index of refraction. Okay, speed of light 3 times 10 to the 8th meters per second. Index of refraction greater than 1. So the ray actually slows down when it's in a material. The wavelength actually changes too. So the wavelength in the material is equal to the wavelength outside the material divided by the index of refraction. So the speed changes and the wavelength changes. The frequency does not change, though. Okay, so keep that in mind when you're looking at these problems. So again, look back at the homework when we talked about this. Don't forget that the speed, I'll just do it in general, the speed is also equal to the frequency times the wavelength. So if the speed gets smaller than the speed of light, the wavelength has to get smaller. It's the frequency, though, that does not change. Okay, very good. Another problem you'll have also from chapter 17, these thin film problems. So we talked about constructive interference and destructive interference. So if it's constructive interference, you will actually see the image. If it's destructive interference, the image is killed off. So non-reflective coating is destructive interference. Hopefully that's ringing a bell. So take a look back through these couple of questions specifically from homework 8. Make sure that you're familiar with those. And for a more detailed analysis here, it's actually kind of a long analysis to look at thin films. Go look back at the concept videos for chapter 17 when I talked about thin films. Okay, so be ready to go with a thin film question. A lot of this stuff you can't rely on intuition at all to come up with this. You've got to really rely on your notes and your experience doing these problems. It's not like velocity, distance, and time. You can maybe kind of try to figure that out. This, you'll be completely lost if you don't make a nice little chart. Okay, so again, a couple of questions from back to homework 8. And then there's one more question here from chapter 17 that I'm going to put on the test, or I did put on the test. A double slit problem. Okay, so light goes through a double slit. There's an interference situation that happens. And here, these are the bright spots. So look back through that section. There's bright spots. Here's the central maximum, bright spot, etc. It keeps going. M is 3, M is 4, etc. Okay, so if it's a two-slit or double-slit problem, this is what we have to work with. This is the physics of it. d sine theta is equal to m times the wavelength, and m is just an index. Okay, so if you knew the slit spacing, that's what little d is, and the wavelength, you can calculate what these different angles are. So theta 1, theta 2, like theta 1 corresponds to m is equal to 1, theta 2 would be this angle, this whole big one here. And then just from the trigonometry, I'll just do this in general, just from the trigonometry, tangent of theta m is equal to ym divided by L. And then m is just that index describing which one we're talking about. So like for theta 1, that was this one, the tangent of theta 1 would be the opposite side. So the opposite side here would be y1 divided by big L. And big L is the distance to the screen. One word of caution, be careful with these things. I mean, the distance to the screen might be in centimeters or meters. The slit separation is going to be really small, so maybe in millimeters. Just be careful with the units. Put everything into meters, and you should be good to go on that. Okay, so you'll definitely see a double slit problem. Double slit, here's really the only two equations that you have. Keep the picture in mind, and take a look back at the homework questions that we did on that. Okay, good. And then we went to, after that, chapter 28, which is called quantum physics, and we looked at the photoelectric effect. So the photoelectric effect, just to give you an idea what the concept is, you shine light on metal. If the light has enough energy, an electron could grab a hold of that energy and be liberated from the surface. Okay, and if there's some left over, the electron gets some additional kinetic energy. So let's see what this means. The kinetic energy that the electron gets is equal to the energy that the photon provides minus the work function. So the work function is kind of like the ticket, the cost of admission. So you have to at least overcome the work function to be able to liberate the photon. So no matter how much low energy light you shine on metal, you'll never liberate any electrons. You have to have an electron with enough energy, and hopefully enough that you even have some left over and it becomes kinetic energy. So the energy of the photon here is hc divided by the wavelength. We've been using this a lot recently. Hopefully you've come to appreciate this. H times c is 1240 eV nanometers. This is really useful when the wavelength of the photon is also measured in nanometers, and then you're just left with eV over here because the nanometers cancel out. But just to refresh your memory what H is, in joules times seconds, it's this number. That's to the minus 34th. And then in EV, it's 4.14 to the minus 15th EV times seconds. So you could just use whatever H that you want, make sure it's the appropriate units, and then you could put in the value for the speed of light, but we've used this shortcut a lot where H times C is 1240 eV nanometers. Okay, so if you needed to find the kinetic energy of the electron that's been released, you could use this formula. You might have to do some algebra, though. I mean, what if they ask for the wavelength? You'll have to do some algebra to find the wavelength. What if you just liberate an electron? You don't give it any additional kinetic energy, you've just liberated it. So to just free it, the kinetic energy would be 0. So if the kinetic energy is 0, so this part is 0, you can solve for the work function. So to just free it, the work function, putting this condition on this formula, is hc divided by the wavelength. And this is the largest possible wavelength that will just free an electron. Okay? This formula is written in terms of the wavelength. Don't forget, you could do it like this too, in terms of the frequency. So work function h times, and this is the cutoff frequency. And that's the lowest possible frequency that this thing will work. Okay, think back to the experiment too. What if you want to stop all current from coming across? So you can turn all of the kinetic energy into electrical potential energy. So using that relationship, we came up with this formula. Kinetic energy, if you multiply both sides by E, would be E times V stop. Okay, so the stopping potential then is maximum kinetic energy divided by the fundamental charge. This little e, just like we've seen really from the first week, is this value. So the stopping potential would be hc divided by the wavelength times little e. I'm really just taking this formula here and dividing it by little e. That's what you're seeing here. Little e is the fundamental charge. And then continuing that work function divided by little e. Now if you want to do it in terms of the frequency, this would be hf minus the work function divided by the fundamental charge. So this, again, that's the work function. Each metal has its own specific work function. Okay, so you'll definitely see a photoelectric effect. You've got plenty of material to look at from the homework, and that was from homework 9. And then we talked about the de Broglie wavelength. So anything that's moving and has mass, in other words, anything with momentum, has its own wavelength. We actually calculated the wavelength of a basketball or something like that with the homework. So this should be a relatively easy problem. This is, if they ask you to calculate the wavelength of something that's moving, this is the only formula that you have for that. Okay, so the wavelength, h divided by the momentum. So P here is momentum. H, this is Planck's constant. We know from physics 220 that the momentum is also the mass times the velocity. Okay, so hopefully everybody gets the de Broglie wavelength problem, gets it correct. This is really the only formula for the de Broglie wavelength. Okay. On the other hand, what if I give you the de Broglie wavelength and I ask you how fast something's moving? Then you'll have to do a little bit of algebra. H over mv. So if you wanted to figure out the speed, multiply both sides by v, and then divide both sides by the wavelength. Okay. And then h is the same thing that I told you before. Planck's constant, and here they are. So by the way, when you're doing the test, make sure you have all these constants ready to go in case you need them. You don't spend your time looking things up. Okay, so 2 questions from chapter 28, 1 photoelectric effect, and then 1 de Broglie wavelength. And then finally, the most recent stuff that we've talked about, this emission spectrum information and quantum numbers. So this was from chapter 29, atoms and molecules. Okay, same idea. You might have even seen this in chemistry. Here's an energy diagram of a generic atom. So ground state, n is equal to 2, n is equal to 3. So these are the excited states. First excited, second excited. So if you're in an excited state, you transition to a lower state. When you do that, you emit a photon. So in this diagram, you can go from 3 all the way to 1, or you can go from 2 all the way to 1, or you can go 3 to 2 and then 2 to 1. So there's 3 possible wavelengths here. Okay, so here's the formula that governs this phenomenon. The difference in energy, so that's the difference between the different levels, is hc divided by the wavelength, or if you want to do it in terms of frequency, h times f. So if you want to calculate the wavelength that's emitted, you take this formula and solve it for the wavelength. So that would be hc divided by the difference in energy. And if you want, 1240 eV nanometers divided by the difference in energy. Again, I've said it several times, but take a look back at the homework. We did problems just like this, actually. It's nice when these energies are in EV, then that makes this calculation a lot easier. So again, take a look back at homework 10 for that. Good, and then the final thing, 4 quantum numbers associated with hydrogen. So we've got the principal quantum number, which is n. This determines the energy. And the n could be 1, 2, 3, 4, all the way up. L is always 1 less than n all the way down to 0. So for example, if n was 4, L could possibly be 3, 2, 1, or 0. Okay? So that's the way n and L work together. And don't forget, if L is 0, this corresponds to the S shell. L is equal to 1. That was P. L is 2, D. So from chemistry, you probably have seen S, P, D, F, and you wonder, where do these come from? Well, it comes from quantum, these quantum numbers. Okay, good. So that's the possibilities for L. M can range all the way from negative L all the way up to positive L. So for example, if L were equal to 3, that would be the F here. But anyway, if L is equal to 3, M could be negative 3, negative 2, negative 1, 0, all the way up to 1, 2, 3. If L were 1, then M could just be 1, 0, negative 1. I went the opposite way that way. Negative 1, 0, and 1. Okay? And then for each of those, you have a plus or minus 1/2. Okay? Good. So, make sure you're familiar with this. This should be an easy one, too, if you're familiar with it. Take a look back at homework 10, where we do several problems like that. Okay. It shouldn't be too bad. I know there's a lot of material, but I've narrowed it down to all this material down to 10 questions, and hopefully this little review gave you an area really to focus on, especially when it comes to the geometric optics chapter. That's a joke. Okay, any questions, just let me know, and I'll talk to you soon.